What's wrong with the atmosphere? Part 2. We're going to discuss the Hunga-Tonga volcano, a warming planet, the PDO, anomalies, sea surface temperature anomaly issues, and a whole bunch more. So hold on to your hats as we dive into this special edition of the Stormsurf Video Surf Forecast.
Stormsurf, waves, weather, buoys, altimetry, snow, temperatures, El Nino, weather analysis, essential data for outdoor people, all the time, no hype.
If you enjoyed the video, give us a thumbs up. If you haven't subscribed, please subscribe. Click the Stormsurf icon down in the lower right-hand corner of your screen. That'll help you get all set up. You get automatic notifications when the videos are posted, typically on Sunday evenings. And if you have a question or concern, and I'm sure you probably will after all we're going to dive into this evening, write it up down below. We'd be happy to respond. If you'd like to make a special donation to the cause, you may. Hit the super thanks button down below, the heart with the $sign in it. With that, I'd like to thank the folks that donated last week. Tim Caston, Our Predicament, Evolution Moto, our longtime contributors, thank you all so much. And then some new contributors, and one sort of not as new because he's donated before. Pierre Morton, Ashi Winshadi, and Mont the Drifter, thank you guys as well. And with that, let's get to work. First off, we're going to take a look at buoys, but we're not looking right at the buoys here for a moment. I want to alert you to a feature that exists on Stormsurf. It's a regional, if you want to call it a roundup of all the buoys. This is for the entire California region. You go right down here. Here's the buoy numbers aligned from north to south. And here, just you can do a quick little look up here on the bars. Gives you an idea of what the surf heights, calculated surf heights be, and then you can click on the individual buoys like San Francisco buoy here, and you can get the data that we're used to seeing. That all is available. In fact, let's go back here. That all available is up here. Just go to the buoy section of the Stormsurf website. You'll see something that looks like this. You scroll down the whole way to the bottom. Right here, California, Pacific Northwest, Gulf of Alaska, and all the buoys show up. So you can enjoy that. We've added some new buoys, too, to the roundup. So we'll start in Northern California, looking at the Point Reyes buoy, number 029. We're looking at all the energy that's hitting that buoy currently, all the way from up to 33.3 second period, really long period energy, which there is none, the whole way down to 5 second period, just pure wind chop. And you can see that's mainly what's going on. A bump here at about 7 seconds, that's like bare minimum wind swell, and then some sort of background swell of undetermined origin in the 13 to 14 second period range. Put it all together, primary swell 5.4 feet at 6.6 seconds from 314 degrees. That makes surf at about 3.5 feet, and that's about what it is, chest high, something like that. And then some secondary swell 2 feet at 10.7 seconds from 297, basically just an extension of the wind swell, and all that longer period, really small energy is just buried. Then here's one of the new buoys we talked about. This is very close to, we'll say, the San Onofre area, Green Beach offshore, number 271. Now you do see a little bit of a bump here in the 15, 14 second period range, and none of the wind swell expected because the Channel Islands block all that. Primary swell 1.4 feet at 14.6 seconds from 184 degrees. That's surf heights in the 2 foot range, and top spots are probably doing 3 feet. And then we go to Hawaii, North Shore, Waimea Bay buoy, number 106. And again, not a whole lot happening here, just a little bit of tiny little wind swell out there. Primary swell, 2.2 feet at 6.2 seconds from 30 degrees. That surf height's of 1.4 feet and effectively not even rideable. So next up, we'll do a quick review of surf heights or significant wave heights for the South Pacific over the past week. And we're just going to blast through this. A little gale did develop south of New Zealand. Peak seas were 37.1 feet here at 51.85 south, 175.2 east, or These are the highest seas over this entire domain. This has produced a small swell that is radiating north and is supposed to hit into Hawaii, I think even as we're speaking, and up into California the early part of the week. That system pushed east and pretty much evaporated. And after that, well, we're into Tuesday. We're already out to Wednesday, the 11th of September. Not a whole lot happening, and that pretty much sets the tone through the rest of the week. And here we are currently with not anything of interest going on down south. Likewise, we're doing the same thing for the North Pacific, again, starting on Sunday, the 8th of September, just rolling through this. Now, there was a little gale that developed north of Hawaii with 16-foot seas aimed at the islands on Monday. Swell hit the islands, but that's all but gone now. Rolling on out here, we're into Thursday, Friday, the 13th of September, and really nothing happened, and here we are currently. So no other swell systems there. We do the same thing for the South Atlantic, again, starting Sunday, the 8th of September, looking for any sort of meaningful. Notice the ice changing here as we run through. This is a Hindcast, so they keep updating the ice coverage every 3 days, and you get a little bit different definition of what's going on. A little bit of a gale here on Saturday with 23-foot seas, southwest of South Africa, but not really a meaningful swell producer, and here we are at current time. Then we go to the North Atlantic, where again, here we are Sunday, Monday, Tuesday, the 10th of September. You know the drill here. Now, there was a small tropical system that organized yesterday with seas. Let's see, we'll go back one. There we go. Was that 18-foot seas out in the middle of the Atlantic? Not good for anybody. That was Saturday, the 14th. That system fade out. Another system spun up here this morning in the North Atlantic, heading towards Europe with 25-foot seas. Can I get one more frame? There we go, 27-foot seas. Then some sort of a disturbance trying to organize off of the mid-Atlantic coast. And then finally, the Indian Ocean. Again, it's going back a week, so we're Monday, September 9th. A broad gale tried to organize south of Australia with 39-foot seas. That faded out, but I think another system, but notice they're sort of falling to the southeast. So not a whole lot happening there. Sideband energy pushing up into Australia, but nothing relative to let's say, Bali and that area. And here we are, current time. Pretty quiet pattern. All right, so what's the forecast look like? And we're going to start up at Jetstream level winds. These winds of about 30,000 feet help support the formation of gales, and when they form, help direct their track. We're looking for a trough, a push in the jet to the south. So this is the North Pacific Ocean. This is the Jetstream here. The Aleutian Islands are right under here. Japan's right there. California here. We see the jet pushing to the south right here. What that helps do is create a counterclockwise flow aloft and also down at the ocean surface. That's the hallmark of low pressure. And of course, low pressure, if it's strong enough, generates winds. Those winds gets traction on the ocean surface and generate raw seas. The raw seas, as they radiate away from the fetch area, the lesser period elements get groomed out, exposing swell. And of course, swell and hit your beach creates surf. We do have a trough. That is the good news. The bad news is it's a backdoor slider trough pretty much all over land. So no real support for swell production is expected, though it has been producing weather in the Pacific Northwest, and that is falling south towards California. The other bit of good news here is the jet is consolidated the whole way across the North Pacific, and it's just barely starting to fall south of the Aleutian Island. We've been hopefully waiting for it to fall even further south to actually get some good exposure, but that hasn't happened as of yet. Let's put this into motion. As we get further into Monday, again, the first backdoor trough pushes into California. Another starts forming off of British Columbia. This one a bit stronger, and with the leading edge of it already into North California by Tuesday the 17th, and then falling south. Notice the whole jet stream starting to fall further south as we get into Wednesday, offering some hope. And with winds building to 150 knots as we get into Thursday, there we go, a certified trough, 114 hours out. Still a bit of a reach, but perhaps, just perhaps, maybe we'll get lucky here and get a a early fall storm and some swell from it. Winds still building as we get into Saturday now with pushing 170 knots. This has some potential, then sort of falling apart as it pushes into the northern Gulf. And here we are a week out with another mini trough trying to organize off of Japan and the Kuril Islands. Surface level pressure and surface level winds. Let's see if what we saw materializing in the jet stream actually shows up and manifests itself down at the ocean surface. You have to have wind blowing on the ocean to generate seas. All right, so here we are Sunday, a pretty placid pattern in control. You see just some mild winds associated with the trough off California. A low starts developing with 18. Oh, that's almost, I'm sorry, that's 30 to 35 knot winds, and actually pushing over the Aleutians up into the Bering Sea. Probably nothing from that. But as we get further into the week, on Friday, we have a little gale in the northern Gulf, a much broader gale over the northern dateline with 35 to 40 knot winds, and holding at 40 knots as we get into Friday night and Saturday. Another one behind that with 45 knot winds, trying to make it to the dateline. We'll see whether it makes it. We'll see whether it even materializes at all. But for the first time, it almost looks like a fall pattern trying to set up, though a bit late. What are the effect of those winds on the ocean surface? This is significant wave heights. Let's roll this out. We know probably not a whole lot initially. There's our first little gale, but most of it's producing seas in the Bering Sea, completely landlocked and of no use to California or Hawaii. But we know there's something more coming behind. And here we go. We see it starting to develop 23-foot seas initially. Now this is almost a week out, Saturday. And that fading. Another system with, what is that, 26? Oh, building to 32 feet. To 35 feet on Sunday, and just barely making it to the North Dateline region before impacting the Aleutian Islands. So some hope finally for the North Pacific. Quick look at the South Pacific. We're just going to roll this out. It literally looks like there's a brick wall under New Zealand. Nothing is getting east of there, at least nothing of any meaningful energy. And here we are, we're almost a week out, not even 24 or 25 foot seas aimed off to the northeast, so no hope there. We go to the North Atlantic, and let's see, there is this little weather system off of the Outer Banks and North Carolina, has produced some fetch and is producing some fetch, but that's quickly to fade out as we get into Monday, Tuesday. Another system, a broad, sort of ill-defined low-pressure system generating, that's probably about 15-foot seas aimed off to the east, good for background swell into the southeast U.S. coast. And then another fetch supposedly developing almost a week out on Saturday off the northeast coast with seas, oh, there we go, about 18 feet and to 20 feet. Now, not aimed so well, but still pretty broad area fetch here. That should make surf from pretty much the whole U.S. East Coast if it materializes as forecast. Something to look forward to, finally. The interesting part is it from the tropics, there is this system. Let's go back here. Now, right here on Saturday, that's almost a week out. Never believe the GFS model when it's going that far into the future, but tropics look pretty dead. South Atlantic, we'll run through this pretty quick. Now, a system here with 33-foot seas, but it's falling southeast, maybe sideband swell for South Africa, and then pushing into the Indian Ocean, producing probably smaller swell aimed off to the northeast. And then we continue on from there. Another system now, this is on Saturday, due south of South Africa with 28-foot seas, but mainly in the 27-foot range, and coming in pretty close proximity to Jeffreys Bay in that area. Certainly looks like some swell would be possible, though, and then things settle down. It's beginning to be the end of the season for the southern hemisphere. The focus is turning north now. And then finally, the Indian Ocean, calm pattern as of right now, but a little bit more energy is supposed to be building under South Australia come Wednesday, the 18th of September. That is 34-foot seas. and definitely pushing energy all up into this area, 35-foot seas, and then even, what was that, 35-foot seas again, and then pushing east of there, and then another system right behind that with in 38, almost 40-foot seas, 41-foot seas. So the season not over for South Australia yet. And even more behind that, 42-foot seas, theoretically a week out, again targeting Australia and sort of leaving the broader part of the Indian Ocean high and dry. Wind forecast for the Hawaii and California area. High pressure in control, northwest winds as of today, blowing pretty hard down. This is the California coast, North California, Central California, Southern California. Trades for the Hawaiian Islands, winds circulating clockwise around the high. Trades 15 knots for the Hawaiian Islands today. Put this into motion as we get into Monday. A pressure gradient develops, building high pressure, low pressure from the trough off the coast pushing inland, producing 20 to 25 knot northwest winds for Northern California, resulting in wind swell. Trades 15 knots for the Hawaiian Islands. So we get into Tuesday, winds back off a little bit, but still 10 to 15 knots along the North and Central California coast. Trades in the 50 knot range for the Hawaiian Islands. Wednesday, another pressure pattern, theoretically falling south. Winds not too bad, 10 knots for Central California, 15 knots for Northern California. Trades for the Hawaiian Islands. Thursday, same sort of pattern, no real minimal wind swell productions. We get into Friday, northwest winds 20-25 knots off of Cape Mendocino, and northwest at 10 to 15 knots for Central California. And trades 10 to 15 knots for the Hawaiian Islands. Saturday, pretty much the same thing. Wind swell production as we get into Sunday for next weekend for North and Central California. And trades relatively light for the Hawaiian Islands. We'll roll this out here one more and more of the same as we get into Monday. It's getting to be that time of year again, so we're going to look for rain pushing into California and snow for the mountains. Maybe, probably not, but you see light rain as we get Sunday night into Monday. A little bit of snow for the highest peaks in the Sierra. Mainly, so those highest peaks would be down towards Mammoth in that area, sort of bypassing Tahoe. Just Mammoth, I think, peaks out at 11,000 feet, and Tahoe peaks out at about 8,800 or 9,000 feet. So, and then another batch of rain coming down the coast, but kind of breaking up, not well organized Wednesday. But you can see again, snow for the highest peaks in the Southern Sierra. The Southern Sierra is the highest part of the entire Sierra range, Mount Whitney there at 14,000 plus feet. So that's probably where you'll see the snow in that area. And then after that, things settle down. We know there is more low pressure. You can see actually snow forecast for the mountains there in British Columbia, northern British Columbia, and then we're 180 hours out and high pressure takes control. The only resort that we found in California that has any snow forecast, Mammoth, was at a couple inches, all on the 18th. So what's that, like Tuesday night into Wednesday, something like that. Snow levels, well, you see this is the base of Mammoth, and this is the top. There is cold air. The red would be liquid precipitation if there is snow. The gray, sleet. The white, actual snow. And the blue is good quality snow. This is 28 degrees or lower. So most of the snow you see would even be confined to, say, 9,000 feet and above, and only in two little windows on the 16th and then again on the 18th. And then finally, the hikers or the backpackers forecast for the intersection of the Pacific Crest Trail and Tioga Pass Road going through Yosemite. You can see it pretty plainly here. Where the road and the trail intersect is about 8,700 feet right here. You can see temperatures. The red line is the freeze line, 32 degrees. Falling down Sunday night, pretty much all Monday into early Tuesday morning. That would be from the first trough pushing down the California coast. Temperatures rebound into the 40 to 45 degree range, then fall down to good hard freezing again as we get into Tuesday night and maybe early Wednesday. Then after that, temperatures rebound and it's almost back to normal, 50 to 55 degrees, maybe even pushing 6 degrees at points. As we get into a week from now, that'd be Monday into Tuesday, the 24th of September. Surf spot forecast. We'll pick Santa Cruz here for Northern California. Surf heights in the 4-foot range as we get Monday into Tuesday. This is all just wind swell. Then another little pulse as we get into Thursday and Friday in the 2.5 to 3 foot range, and then 3 feet. Now if this is wind swell, it's probably not wrapping into most breaks in Santa Cruz. You'd have to go up the coast some, and this is probably valid for Ocean Beach and San Francisco area as well. Swell heights 4 feet at 9 seconds. You do see bits and pieces of southern hemi swell from that gale that pushed under New Zealand, trying to hit on Monday. It's about 1 feet at 17 seconds. There you go, 1 feet at 16.5 seconds into Tuesday, and 1 foot at 14 seconds on Wednesday. And then your more wind swell mixed in, 3.5 feet at 8 to 9 seconds. So nothing too remarkable. We go to Dana Point, Southern California, protected from the wind swell. There is the southern hemi swell, but you see surf heights in the 1.5 foot range at best and down from there. And the southern hemi swell, well, this is not the actual swell. It doesn't even show up on the chart, but it would again be in the Monday, Tuesday, Wednesday time frame. And swell heights 1.5 feet at 16 seconds, something like that. So 2 foot surf, maybe 2.5 feet. And nothing really after that. South shore of Oahu, surf heights 1.5 feet, maybe 2 feet if you get lucky. There is some of that southern hemi swell supposedly hitting the south shore now, but it doesn't even show up on the chart. There's just more wind swell than there is anything in the 2.5 foot range at 8 seconds. That really isn't too much. I'm going to go over to South Africa, Jeffreys Bay. Surf heights, well, 10, 12 feet, 15 feet, fading as we get in later in the week down to 8 feet. And then another big potential bout of swell in the 25-foot range. Now, it's not that big, actually, at Jeffreys Bay. That's off the coast. But you get the general idea here, the trend. Swell heights 10 feet at 12 seconds. Not the super long period stuff like we were getting earlier in their winter, and then falling to the 6 foot 11 second range, and then 15 feet at 14 seconds towards Sunday a week from now. Then finally, Bali, surf heights in the 5 foot range, falling to 4 feet, hanging in about the 3.5 foot range, maybe building again to 5 feet towards the latter part of the week. Swell size is 3.5 feet at 14 seconds. You can read the numbers, 2.5 feet at 13 seconds. Clearly, the southern hemi is in the latter parts of its winter, or spring for that matter, and starting to lose its energy. And now for our special presentation. We are not doing the regular MJO-ENSO discussion, but we're going to talk about what's wrong with the atmosphere, or maybe what isn't wrong with it, but sort of a deep dive into some of the other long-term oscillation and components that influence our weather long-term. Enjoy. Last week, we discussed a bit about what's wrong with the atmosphere. Why is, one, the southern hemi not doing what we thought it would do this past summer in terms of swell production? And why is the northern hemi not really waking up as we expected it would about this time of year, which it normally does by September? Still, a very quiet pattern is in play. All right. And we focused a lot on the MJO and why the MJO is not as active, not as present as we thought it would be, either towards a inactive pattern or an active pattern. And the net conclusion was we're caught somewhere in the middle, in between the active phase of the MJO, the inactive phase of the MJO. El Nino and La Nina, we're in this transition, and there isn't a lot of momentum in the atmosphere. The pendulum isn't swinging hard from El Nino to La Nina, from the consistent active phases of the MJO to consistent inactive phases of the MJO, and we're just kind of caught in this dead zone in between. And one thing that I meant to mention last week and didn't was the Hunga-Tonga volcano. So this portion of the video is going to be dedicated to discussing that. On January 15th, 2022, the Hunga-Tonga volcano erupted a good bit east of Fiji, and this was different than most volcanoes because it was underwater. That is, the explosion, the eruption of it had to go through a lot of ocean water before reaching the ocean surface, as compared to, let's say, Mount Pinatubo in 1991, which was an above land volcano. When it erupted, it put massive amounts of aerosols up into the upper atmosphere. By aerosols, we're talking literal particulates of matter high up into the stratosphere, and that in turn helped cool the planet down. These aerosols, they reflected literally sunlight. We've talked about outgoing long-wave radiation. Well, this was a volcanic caused outgoing long-wave radiation event. That was Mount Pinatubo, which caused, again, massive amounts of reflection of sunlight, cooling the planet down for years afterwards, sort of like a long-running La Nina pattern. Now, the issue was with the Hunga-Tonga volcano, it was all underwater. And so the massive amount of heat that it was created in the eruption vaporized the water above the volcano and then sent that in turn way up into the stratosphere. By stratosphere, we're talking starting at jet stream level, so let's say roughly 30,000 feet and above. Now that in turn, though they are not aerosols, the water droplets high up into the atmosphere do help reflect sunlight. I don't think quite as much as aerosols, and this is where the science is a bit murky, because no one knows exactly how this is going to play out, because we've never seen an undersea volcano erupt during the satellite era when we have great instrumentation. And so this is, again, a case of a learning experience. 2, can the models handle that? Someone made a comment about that last week as well. The answer is probably not, okay? Stuff happens, and we try to account for it as best we can in the models, but that isn't always the case. Now, so let's go and try to dig into just a little bit of some of the data around this volcanic eruption and what impact it might have had. Here's a chart depicting, this is at the 10 millibar level. This is like the jet stream is at 250 millibars. Surface is down at 1,000 millibars. So this is way up in the stratosphere. And you can see just year by year by year, they're tracking the amount of H2O, water vapor, in the atmosphere. Going back here, this is 2003. You see a little bit of a bump here in 2013. And then you get to January of 2022, and bam, just the stratosphere is obliterated with water vapor. So as you can see, we're going now to February of 2022. This is that stratospheric water vapor encircling the planet pretty much on the equator near where the volcano was. But as you get into February, April, you see pretty much the same pattern, if anything, only getting stronger. You get into June and notice that it's starting to fall south. September, even further south. October, pretty much isolated to entirely the southern hemisphere. And by December of 2022, fully down over the southern hemisphere. And the suspicion is, though I don't have data, is one, it's still sitting there today. The question is, how long will it last? I've seen estimates anywhere from 2 years to 10 years. It is, again, we are in uncharted territory. We do not know. But if you recall, as we were watching the development of El Nino this past winter, we noticed an interesting anomaly, especially in the southern hemisphere. It just seemed no matter what we did, and we thought the Southern Oscillation Index would be falling. In fact, let's go look at the data. As our El Nino was developing right here, and you see the Southern Oscillation Index, difference in pressure between Darwin, Australia, and Tahiti, pressure was falling. But then we got into like the June, July timeframe, and here is the neutral range, neither La Nina or El Nino. We hit this bump, or this speed bump, and then our El Nino tried to get going, as it typically does, strongest as we get into the fall months, but never really dipped as low as we thought, and then pretty much was over before it began. And there were these constant rumors about the pressure in the southern hemisphere being higher than normal, which we kind of just saw there in that image. Not, there's not hard data on this, but the general tendency was that the pressure, even in the entire Pacific Basin, was higher than normal. And what might have that come from? Well, if you have more aerosols in the upper atmosphere and you have more reflection of sunlight, that doesn't promote warming. Even in a warming planet, that doesn't promote cyclonogenesis. It doesn't help support the formation of storms as much as one normally would have expected in a quote-unquote normal environment. Now, part 2 of this is global warming. And probably one of the, maybe controversial, but one way of measuring the effects of a warming planet is the amount of carbon dioxide in the atmosphere. So here's a graph, fairly recent graph. Today's value, 425 parts per million of CO2 in the atmosphere. 10 years ago, we were at like 389, and you see the general trend here. And I'm not going to get in to try to debate whether it's real or not real. For the purposes of this discussion, CO2 levels are for sure increasing, and I think, well, let's just go look at one more chart. And at the same time, monthly, or in this case, monthly global temperature anomalies have increased as well. And you can see pretty here, this is the 40s and the 50s, and right here is 2024. This is average temperature anomalies around the planet. Yes, you can sort of argue about, well, how do they get the data and that sort of thing, and I don't have all the details, but a clear trend is upward temperature anomalies coinciding with upward CO2 levels in the atmosphere. And of course, the theory being CO2 is a greenhouse gas, that is, it traps heat in the atmosphere. Now you go, no, wait a minute. The charts you were just showing us due to Hunga-Tonga showed more aerosols in the atmosphere, more water vapor displaced in the southern hemisphere, which theoretically should be cooling things down. And that is true. But in contrast with it, this is not a one-dimensional picture. We are playing 5-dimensional chess here. There is the background warming effect of CO2 in the atmosphere, and these two cycles, just like El Nino, La Nina, the MJO, and the PDO, are all interacting with each other all at the same time. And now you got a hint of where we're going with all this. So as the planet warms, warmer air can hold more moisture in it, and then theoretically you get a wetter atmosphere. This chart here depicts monthly global precipitable water. Okay, what does that mean? That is, if you take any spot on the Earth and you basically build a logical column from, let's say you live in San Diego. We're just going to go straight up in the atmosphere the whole way up to the jet stream, and you measure all the water in that column of air. And then you do that the whole way around the planet, and you do it over time, day after day after day. In this case, this is we're looking at the months of July and August, but you see as you go through different months of the year, there's more water in the atmosphere. A lot of that has to do with the seasons too, right? If the sun's beating down, warming the atmosphere, then the atmosphere can hold more water. But the trend over time is from less water in the atmosphere to more water in the atmosphere. And this is not in the stratosphere. This is below, this is in what they call the troposphere, from the jet stream level on down to the ground. So more water vapor in the stratosphere due to the volcano, more CO2 into the atmosphere, mainly the lower atmosphere, warming the planet, more water vapor in the atmosphere, providing more opportunity for rainfall when that rainfall can happen. And then as the atmosphere warms, well, then ice has a harder time, like glaciers, like ice sheets in the Antarctic, that theoretically would there'd be less of it. So this is a measure of Arctic sea ice volume by year. They measure it by satellite, so it's extremely accurate. Here is back in the 1980s, the 1990s, the whites are 2000, the reds 2010, here's 2024. You know, you pick your month wherever you want. There is just less Arctic sea ice volume by year, measured by a satellite. And then here is sea surface temperature anomalies by latitude. So the Arctic here, the Antarctic here. Here's the dividing line between temperatures getting colder or getting warmer. The trend you can see is warmer in all cases, but most of the warming appears to be happening in the Antarctic, where in the Arctic, it's something less. Now, what's really even more kind of twisted and weird is it seems like the ice sheet is melting quicker in the Arctic as compared to the Antarctic, and I don't have an explanation for that, but I do know that it's happening. And then finally, average global atmospheric moisture in August, all right? And this is a little bit of a combination of both the two topics we were talking about, the volcano and a warming planet. Again, the warmer the air, the more moisture you can hold. And so they've been measuring that. You can see there's sort of the median is right here, a little bit lower, and this is going back to the 40s, a whole way up into the 80s, 2000, 2010, 2020, okay? And you see the background state of generally more atmospheric moisture, and then you have the volcano here that just completely pushed it up higher than it's ever been before. The assumption being that at some point in time, the moisture injected into the stratosphere from Hunga-Tonga will eventually fade out, and I wouldn't call it evaporate. And honestly, that moisture in the upper atmosphere turns into ice crystals. It's not literally liquid. And it doesn't rain out of the stratosphere either. It dissipates effectively. It just gets caught in the basic circulation of the planet and fades out. Again, the question is, how long is that going to take? But what the net effect is that does have a cooling effect on the planet, which sort of mimics a little bit of a long-running La Nina pattern. And then, of course, there is the PDO. So we're talking cycles on top of cycles on top of cycles on top of cycles, all interacting with one another. But in my mind, the largest cycle is what we call the Pacific Decadal Oscillation. This is just a value, but what it generally is describing is high pressure in the Pacific, higher than normal Pacific pressure in the Pacific, or lower than normal pressure. When it goes into the blue, the cold phase, that generally is considered higher than normal pressure in the Pacific. When it's in red, that's considered lower than normal pressure. The reds would then be like long-running El Nino patterns, and the blues would be long-running La Nina patterns. And you can actually tease this out. So you can see there's a long stretch here. In fact, maybe I can blow this up a little. Oh, you can see it. Actually, the balance of blues started in July of 1998. And it is no surprise that in January, 97, 98 was a super El Nino. And then ever since then, since, according to this index, April of 98, we've been in the cool phase of the PDO ever since. So let's zoom in just the past couple of years here of the cool phase of the PDO. Here we are, April 2020. Here is, let's go to specifically, and this is kind of interesting, but right about here, January 2022, when Hunga-Tonga did its thing, all right? Now you go, well, maybe that's helped pushing the PDO even colder. But you see, as we can go month by month by month, and really the whole way through the year, there's no noticeable change in the depth of the PDO in the Pacific due to Hunga-Tonga. That said, it's not going anywhere at all. And even as of June of 2024, we're almost as negative as we've ever been, minus 3.16. Here was the other big one here, 3.13. So the cold phase of the PDO is not changing, but at the same time, we're not seeing any additional energy being given to it from the volcano and its aerosols and all that sort of thing. But it's not helping it back off any either. Let's go look at a broader time frame now. Has the PDO been colder than what it is right here? Well, here's -3, right? Well, we see back in 1954 in that area in the 50s, about as cold. Now, I don't know how accurate this is going back to the 1800s. It's from reconstructed data, and I think that's oh, actually, I shouldn't say that. A lot of this, I think, is from actual pressure measurements, just like the Southern Oscillation Index. They have a 200-year running record of actually people measuring with barometric pressure gauges. So I think a lot of this comes from that as well. So you get the general sense of where we are now is not really any different from events that have happened in the past. There is a lot of variability. That said, we've been waiting for the PDO to go warm. It always, let's see, what's the saying go? Yeah, it's the calmest right before the storm, or if the storm can't get any worse, maybe it's about over, sort of thing. So we're watching that. The point being, can we conclude anything from this? And there's yet one more piece to this puzzle. Sea surface temperature anomalies. You've seen this before. This is based on a 30-year running average temperature for every, they call them gribs. It's, say a 1 by 1 degree box over every square inch of the planet. You take that data year after year for 30 years, and you get an average, and you update it. I don't think it's monthly. I think it's something less than monthly, but you take the average temperatures, they're not daily though, let's say once a week, okay, over the entire planet, over 30 years, and then you compare what the ocean is today compared to what it is that 30-year average, and then you get a variation from normal. And here's our current one, as we've discussed before, with the emerging La Nina pattern. Now, the thought is, and I've seen this a couple of places now, is that a 30-year running average is maybe too long. NOAA's trying to be conservative. They're trying to make sure, a lot happens. There's a lot of variability from year to year, and there's volcanoes, and there's, forest fires, and there's all this stuff that all play into the interaction of the atmosphere to define, quote unquote, what is normal, okay? And so a 30-year average tries to wash out some of those one-time special events to get you a true average. But what the thought is that because the planet is warming, again, you saw the CO2 level increase, the ocean temperature increase, and all that sort of thing going on, that 30 years is maybe too long because the temperatures are warming quickly. Too much of this represents what has happened in the past when the planet was cooler. So you notice how everything's yellow? That's kind of, well, yeah, of course everything is yellow, because 30 years ago, the planet was a lot cooler. So there is an alternate chart, and it is the global mean sea surface temperature anomaly. So I actually wrote Alex to try to get a little bit, this is from cyclonicweather.com, to get exactly, well, how is this chart produced? But I think it's literally 1 year of data. Here is the average temperature over the entire planet today, grib by grib by grib, and how does what's happening right now compare to the average temperature? I know that's not a very good explanation, but what it does is it sort of washes out that extremely, in fact, let's go look at it. There's the extremely warm image there. Here is more a relative speaking to where we are today. Certainly not perfect. You still get the warm spots here and here, and then the La Nina signature here as compared to, there's your La Nina signature, there's your warm spot, there's your warm spot. But all this sort of moderate warming that's happening, is washed out, and you get more of a normalized sense of, well, if you even compared it to 30 years ago, how are we doing? We're still in some flavor of La Nina, but you don't get that You still do. Actually, look at this. There's a fair amount of warming everywhere, but not as bad as before. And I think part of NOAA and the National Weather Service challenge is to come up with some sort of an alternative view of how to classify El Nino and La Nina in a warming planet. In fact, I've even seen some discussion now about just measuring in one little area, which is what we do, the Nino 3.4 region from 120 west out to 170 west, 5 degrees north and south of the equator. You need some sort of a broader, more comprehensive way of measuring the strength of El Nino or La Nina, given that everything is getting warmer and our base state is not what it was even 10 or 15 years ago. So, what does all this mean? It's very difficult to tease out what the volcano, global warming, the PDO, and even the data that we're using, how that all integrates to tell us, well, does that give us any clues as to what's going on right now in the Pacific Ocean in regards to storm production? And does it inform us on what's going to happen in the future regarding our winter and rainfall and the strength of the MJO and the strength of a pending La Nina? I think the shorter answer is we can make some generalized guesses. And some of that's informed by the models, but some of it's also just sort of, how do they do it? Put your thumb up, feel the wind and make a guess. And my guess is we're probably not too far off the mark from what we were saying before. I think that given the Tonga aerosols, that pushes us towards a colder sort of regime. Given the PDO, that clearly talks about being colder. Given the water vapor lower in the atmosphere due to the global warming signal, that suggests more of a warming pattern. But I think the long-running PDO kind of washes some of that out. And again, I'm going to stick back with what we talked about last week. What's wrong with the atmosphere? Well, I just don't think there's a whole lot of momentum. There are a bunch of other mitigating factors going on, but I think it's a transitory thing that we're in. That said, do I think this winter is going to be some sort of an epic surf winter? No, I don't think so. I think La Nina is still happening. In fact, we've gotten a bit of a pulse, as you saw earlier, in La Nina, and that it's trying to find its legs. It's because we're in the change of season, typically, just like El Nino in the fall, that's when La Nina wakes up too and starts showing its teeth. And it's trying to do that, not particularly strong at the moment. I still think we're going to have some sort of La Nina, but at the same time, I'm not seeing any evidence of some major La Nina. That said, I've looked at other models, and we could go and spend another 15 minutes looking at models all over the planet, and some of them say, well, it's pretty dry in California and certainly across the whole southwestern U.S., and that's from the European model and some others. And then I see other models that say, well, maybe not. So it's too early to know. I'm going to go with my original prediction, though, that suggests some sort of a weak La Nina and probably not a super wet winter in California. I was thinking 85% normal of precipitation. That, in this year in terms of snowfall and rain, maybe that is a little overly optimistic. But certainly more of the rainfall and the snowfall will be north, up in the Pacific Northwest and up into Canada. Surf-wise, high pressure seems to be the name of the game, and it has been even last year during La Nina. Even during our El Nino winter, we had a whole bunch of storms, but they were all right on top of us. They weren't out in the central Pacific, out towards the dateline or north of Hawaii and the Gulf of Alaska. And yeah, we got surf, but it was a blown out mess half the time because everything was real local. And that speaks to high pressure, again, being centered right over the general pattern of high pressure over the dateline, forcing the jet stream right into us and not allowing it to ridge further north and all that kind of thing. So for this coming winter, we'll see how it plays out, but I think La Nina is going to be the major driver. And I think this pattern that we're in eventually will wash out, and that we'll get into some sort of a surf pattern of meaningful nature. And the models are trying to hint at that. I think this is a temporary issue. Well, I hope you enjoyed that. With that, it is time to wrap it up for the evening. Looking at the models, it looks like finally the North Pacific is trying to come online slowly, haltingly, and behind schedule, but that is probably not unexpected given we have some sort of a building La Nina pattern. How strong, yet to be determined. So if you enjoyed the video, give us a thumbs up. If you haven't subscribed, please subscribe. Click the Stormsurf icon down in the lower right-hand corner of your screen. If you have questions or comments, write them up down below. And again, if you'd like to make a contribution to the cause, you may hit the super thanks button down below, the heart with the $sign it. So that's it for this week. We will do this again next week, same time, same channel. Thanks for watching, and we'll see you again soon.